Okay, so welcome everyone to today's Virtual Digital Economy Seminar. It's great to see so many familiar faces again. The moderator today will be Hannes Ulrich at the University of Copenhagen and DRW Berlin. He'll introduce our speaker momentarily. Let me just remind you about the format. If you have any clarifying questions during the talk, please post them in the chat and Hannes will manage the queue and unmute you so you can ask the question directly. We'll also use the same channel to collect questions for the Q&A after the talk. As always, today's session will be recorded, but we'll also stream on YouTube. So if you do ask a question, then you will appear on the live stream and in the recording. Without further ado, very happy to hand over to Hannes.
Thanks, Christian. So I'm very happy to welcome our guest today, Ashesh Rambachan, who is at Microsoft Research in New England. Ashesh is coming from the younger generation, but he already has a very impressive list of publications and pipeline in the area of causal inference and data-driven decision-making, which I think is a super timely and very important, very broad topic. So he's contributed to methods and also has really amazing applications. So today's talk will be about identifying prediction mistakes in observational data. And Ashesh, you have 45 minutes and then roughly 50 minutes of Q&A. I'm very happy to have you here. The screen is yours.
Awesome. Thank you. Thank you very much. I'm really excited to get the opportunity to speak with you all today, especially the last seminar of the year right before Christmas. So thank you guys for joining in to listen to this talk. So I'll be talking about this paper identifying prediction mistakes in observational data. So let me just start with some high-level motivation for the questions that I'm thinking about. So expert decision makers must often make consequential decisions based on the prediction of an unknown outcome. And these settings are ubiquitous throughout economics. So let me just start with a few examples. First, in the criminal justice system, judges decide whether defendants should be released prior to their trial based on a prediction of whether they will fail to appear in court. In the healthcare system, doctors decide whether patients should be diagnosed or tested based on a prediction of whether they suffer from some underlying medical condition. And then finally, as one last example for now, in the labor market, managers decide which job applicants should be interviewed or hired based in part on predictions of their on-the-job productivity. Across all of these domains and many others that we can come up with, a common set of core questions arise. Do these expert decision makers make systematic prediction mistakes based on the available information in these repeated high-stakes environments? If so, which decision makers, on which decisions, and in what ways are their predictions systematically biased? Now, of course, these are foundational questions in economics, but they have newfound policy relevance as data-driven algorithms now inform or replace expert decision makers throughout the economy. So across all of these settings that I briefly mentioned, computer scientists and data scientists are actively designing and implementing data-driven algorithms that use historical data to make predictions to, in turn, replace or complement existing decision makers. So as a result, there is newfound policy relevance in evaluating the quality of expert prediction in order to inform the design and implementation of these data-driven tools. Yet, uncovering whether a decision maker makes systematic prediction mistakes in these settings, which are far removed from controlled lab or field experiments, is at its core a challenging econometric problem for three reasons. First, the decision makers may observe private information, additional information that is unrecorded in the data, but relevant to predicting the outcome. Second, the decision maker's preferences over choices and outcomes are unknown and may richly vary across decisions. And then finally, the available data suffers from a canonical missing data problem. We only selectively observe the outcome conditional on some of the decision maker's choices. So, in light of these challenges, how can we ever really tell whether a decision maker's choices reflect systematic prediction mistakes rather than optimizing behavior at unknown preferences and information sets? Now, while empirical researchers may recognize any one of these challenges in analyzing specific empirical applications of interest, they typically address them by either resorting to strong assumptions or by developing carefully crafted structural models that are tailored to the problem at hand. So for example, some empirical researchers in economics and computer science attempt to directly compare the observed choices of an expert decision maker against those that would be made by some algorithmic decision rule, but do so under assumptions that restrict preferences to be fixed across all decisions within a decision maker, all decision makers within a population, or assuming that the observed choices were as good as randomly assigned, conditional on the recorded features, assuming away the problem of private information. And more recently, economists have attempted to analyze decision-making behavior by writing down parametric structural models of decision-making that assume that the decision maker's information set can be summarized by some known parametric distribution. So in light of these challenges, what is missing is a unifying econometric framework to study the identification, characterization, and how we can conduct statistical inference on systematic prediction mistakes under weak assumptions on preferences and information sets that can be implied in these sorts of observational settings of interest. So what I'll do in this paper is I'll propose exactly such an econometric framework rooted in microeconomic theory to analyze decision-making behavior in these sorts of applications like pretrial release, medical diagnosis and testing, and hiring. In doing so, I'll clarify what can and cannot be identified about systematic prediction mistakes from data and empirically relevant assumptions about behavior. I'll show how data and these assumptions can be mapped into statistical inferences about systematic prediction mistakes. And then finally, I'll argue that these results are tractable and can be used to analyze real-world empirical applications. And I'll illustrate that through an application to the pretrial release system in New York City. And then finally, with whatever time remains at the end, I'll try to close the loop and come back to the original policy motivations for these questions about systematic prediction mistakes, and hopefully show you that this sort of econometric analysis of choice behavior can help inform the design of algorithmic decision systems. And in particular, they can help us think about whether we should be deferring to versus automating existing decision makers, which is sometimes referred to as the problem of algorithmic triage amongst computer scientists. So with that overview in mind, let me now try to make the setting a bit more concrete by starting to introduce some notation. So I'm going to be focused on a setting where there is a single decision maker that makes many decisions. And each decision is going to be summarized by some recorded characteristics X that are observed by the decision maker at the time of their choice and are recorded in the data so we get to observe them as well. So in this running pretrial release example that I'll return to throughout the talk, there, the decision maker is a judge who will decide whether to release or detain many defendants. And each defendant is going to be summarized by some recorded characteristics X, such as their current charge information, their entire prior arrest record, and possibly some demographic information that are available to the judge at the time of their choice and are recorded in the data so we get to observe them as well. Next, for each decision, we're going to observe the decision maker selecting a binary choice. So therefore, from the joint distribution of the observable data, we can identify the decision maker's conditional choice probabilities. In the pretrial release example, this is nothing more than the judge's conditional probability of releasing a defendant as a function of these observable characteristics. Now, in the talk and the main text of the paper, I focus on the leading case where the decision maker's choice is binary, but my results generalize to settings with multiple choices, and I discuss that in an appendix of the paper. Finally, each decision is going to be associated with some latent outcome Y star that's possibly vector valued that's unknown to the decision maker at the time of their choice. Here, we, the researchers, are going to face a missing data problem because we'll only observe this latent outcome Y star if the decision maker selects choice C equal to 1, but not if they select choice C equals 0. So throughout the slides, you'll see some standard notation where I'll then write the observed outcome as Y, which you can think of as the product of the decision maker's choice and this latent outcome. So going back to that pretrial release example, there, the latent outcome is often simply defined to be whether a defendant would fail to appear in court upon release. And we mechanically only ever observe this outcome for a particular defendant if the judge decided to release them. Then just a flag, in the talk and the main text of the paper, I'll assume that the decision maker's choice does not have a direct causal effect on the latent outcome and only generates this missing data problem through this form of one-sided selection. But that's a special case of the more general analysis of treatment assignment problems that, again, I provide in an appendix of the paper. So Because of the missing data problem, only the conditional distribution of y star given choice is 1 and the characteristics x is identified from the data. But the conditional distribution of y star given choice is 0 and the characteristics x is unidentified. And as a result, the conditional distribution of y star given just the characteristics x is partially identified. We can only learn this object up to a set without introducing further assumptions. So going back to that pretrial release application one last time, there we can observe the failure to appear rate among released defendants, but not detained defendants. And as a result, the failure to appear rate among all defendants is partially identified. Again, we can only learn that object up to a set unless we introduce further assumptions. So altogether, for a single decision maker, we're going to observe a data set that consists of each decision they made. For each decision, we're going to observe its characteristics x, the decision maker's choice c, and if the decision maker selects choice c equals 1, we're also going to observe the latent outcome y star. Now, for much of the talk, to focus on the identification problems in this setting, I'm going to assume that we know the joint distribution over the decision maker's choices exactly to focus on the identification challenges again. But when we come to statistical testing, we're going to imagine that we have n IID samples from this joint distribution. So in this setting, to analyze those motivating questions about systematic prediction mistakes, I'm going to analyze the decision maker's behavior through the lens of a benchmark non-parametric model of subjective expected utility maximization, which will analyze the decision maker as if she makes choices to maximize expected utility given any subjective beliefs about the latent outcome y star, given the characteristics x, any utility function defined over choices, outcomes, and characteristics in an admissible class, and then any additional distribution of private information. I'll then ask 2 questions. First, can we statistically test whether the decision maker's subjective beliefs about the latent outcome given the characteristics x are accurate? So now recall that due to the missing data problem, the true conditional distribution of y star given the characteristics x is partially identified. So I'll say that the decision maker's beliefs are accurate if they lie anywhere in the identified set for the true conditional distribution of y star given the characteristics x. If not, I'll conclude that the decision maker's choices reflect systematic prediction mistakes.
Ashesh?
Yep.
There's a question by Coleman. Coleman, do you want to unmute?
Yeah, so real quick question. As I understand it, the characteristics X are exogenous. And I'm wondering, maybe this is more pointed towards when you would get to an algorithmic decision maker. Would if the forecast is about another individual's decision, like in this bail example that you're looking at, couldn't the defendant game the algorithm, however the decision maker makes decisions to try to take advantage of that?
Great question. So we can come back to this to sort of talk about it more concretely when it comes to the empirical application. But sort of in the empirical application of pretrial release, typically what the algorithm is predicting is it's a prediction of whether or not someone would fail to appear if you decided to release them based on observable characteristics such as their current charge and other information in their charge, basically criminal record. So the question you're asking is, well, suppose is there some way that a defendant or a judge or even a prosecutor could sort of game the way they're charging defendants to try to manipulate the algorithm? That is an important question. There's a large literature basically in computer science called strategic classification, strategic regression, which asks, if I knew in advance that people were going to be gaming or manipulating my algorithm by manipulating their characteristics, how would I alter the way I would estimate the prediction function in the first place? So for the purposes of this talk and this paper, I'm going to, when I come to sort of that policy application, I'm going to be sort of ignoring those strategic possibility in this setting. I think there's a strong argument of why that's really not a concern in the pretrial release system. So in other words, what I'm going to be doing is I'm going to be asking, if you took the historical data, estimated a model to predict failure to appear risk, and then simply asked on the cases that a particular judge observed, does that algorithm beat the judge or does it beat the judge on specific subcases? But it's an important question, and I think it becomes sort of first order if you go to sort of hiring applications or maybe even some medical context as well. But we can come back to that when it gets to the application.
Maybe because we have a quick break, Elliot, you can go ahead and ask a question.
Oh yeah. Oh, thank you, Hannes. Hi, Ashesh. So
Hey.
maybe you'll get to this a little bit later, but if you're going to infer accuracy of beliefs from the decision, then how is this going to address this issue of, like, judges' preferences? Judges might have some preferences over unobserved variables, like, the defendant has kids or, extended family or something like this. That might be due to preferences, but you would infer that as being inaccurate.
Great question. So that this question of under what conditions can we separate out whether choices are being driven by preferences or inaccurate beliefs is going to be sort of the core problem I'm thinking about in this paper. So what I'm going to do is I'm going to ask if we have a conjectured class of utility functions over which we think the judges may be making decisions. So in other words, their payoffs are summarized by something in that class. Under what conditions can we basically test that there exists no preferences in that class to rationalize behavior? So I think what your question's getting at is, if we worry that preferences vary based on some unobservable, how would that affect the conclusions of sort of the test I'm ultimately going to propose? So a brief preview is that the sorts of unobservables that could be affecting payoffs that would generate the violations that I'm going to talk about later on in maybe like 10 or so slides actually have to take a very particular form in how they're affecting the decisions. They effectively have to be generating sort of a Simpson's paradox on the decision maker's choices. So in the pretrial release application, it means it has to be making judges simultaneously more lenient while also making defendants more risky, or making defendants less risky while making judges more strict. And most of the examples people come up with about omitted payoffs bias in the pretrial release system actually don't satisfy that condition. So something like whether a defendant has a large family would typically, I think our prior belief would be that would make a defendant less risky. They're less likely to run away because they have a family in the area, but that would also be making the judge more lenient in our typical intuitions. But sort of what's nice, what I find valuable about thinking about this from an identification perspective is it now places a lot of structure on the types of sort of stories we would have to tell if we want to overturn conclusions about prediction mistakes.
That's helpful. I guess I think age is an example that satisfies that category, but I guess that's observed. So
so basically what I'm going to ultimately do is I'm going to say, if it is observed characteristic, we should allow preferences to possibly depend on them, and then ask what are the testable implications given a particular choice of what we say judges care about. And then practically, we should be reporting sensitivity analyses on how sensitive are our behavioral conclusions to those sorts of assumptions in this pretrial release application. When I do that, I find that the conclusions are relatively insensitive to sort of common choices.
Okay.
Yeah. Great. So I'm going to ask, can we test whether the decision maker's implied beliefs are accurate? Meaning, do they lie anywhere in the identified set for this true conditional distribution of y star given the characteristics x? And if not, I'm going to conclude that their choices reflect systematic prediction mistakes. And if their choices reflect systematic prediction mistakes, I'm then going to ask, can we conduct inference on parameters that summarize the extent to which the decision maker's subjective beliefs are systematically biased? So as folks have alluded to, sort of the core challenge here is going to be to somehow make statements about the decision maker's implied beliefs about y star given the characteristics x using data from the joint distribution on their discrete choices and selectively observed outcomes without exact knowledge of their utility function, and importantly, leaving private information entirely unrestricted. So at a very high level in tackling this problem, the paper makes several contributions. The first is I provide a complete empirical characterization of whether the decision maker's choices are consistent with expected utility maximization at accurate beliefs. Then over a benchmark class of utility functions, I'll show that identifying systematic prediction mistakes, falsifying whether choices are consistent with expected utility maximization at accurate beliefs, requires us to introduce two additional assumptions. The first are econometric assumptions to deal with the missing data problem. And the second are going to be behavioral restrictions that restrict the richness of the decision maker's utility function. And I'll define that more precisely later on. Then under those assumptions, we can test for systematic prediction mistakes using quasi-experimental variation to develop informative bounds on the missing data, out of sample prediction as an intuitive form of dimension reduction, and then test based on moment inequality procedures. Second, I'll show also that under those same assumptions, we can go even further and characterize the ways in which the decision maker's predictions are systematically biased. Now, I probably won't have time to talk about these results in depth, but at a high level, I think about this in two ways. The first is to summarize the magnitudes of the decision maker's systematic prediction mistakes and show that we can bound how common and how costly are the decision maker's systematic prediction mistakes to themselves at their own implied preferences. The second is I'll show that we can also start to get at the mechanisms and show you that we can bound a parameter that summarizes the extent to which the decision maker's beliefs overreact or underreact to variation in the characteristics, which again may be suggestive of behavioral mechanisms in these settings. So altogether, this set of econometric results enables researchers to test for systematic prediction mistakes under what I'll argue are weak assumptions, characterize the properties of the decision maker's implied prediction mistakes, conduct statistical inference on their conclusions, and then coming back to Elliot's question, and what I think of as most important, is now concretely report sensitivity analyses on the robustness of our behavioral conclusions to alternative econometric and behavioral assumptions in these settings. Then taking these results, I'll show that we can actually use them to analyze a real-world application. And in particular, I'm going to ask whether judges in New York City make systematic prediction mistakes about defendant behavior in their pretrial release decisions. I estimate as a lower bound that at least 20% of judges in New York City make systematic prediction mistakes about the probability defendants would fail to appear in court. These prediction mistakes overwhelmingly arise on defendants at the tails of the predicted risk distribution and over Black defendants, and appear to occur because judges' implied beliefs systematically underreact to variation in failure to appear risk that is predictable based on defendant characteristics. And then finally, motivated by those behavioral findings, I come back and ask what would be the effects of replacing judges with an algorithmic release rule in New York City. And I find that replacing judges who made systematic prediction mistakes in the sense that I define in this paper dominates the status quo in a robust manner. So therefore, the behavioral analysis of expert decision makers that I've defined in this paper can help us think about the design and implementation of data-driven algorithms in these settings. Now, let me just start diving into sort of the meat of the talk. So I'll skip over the related literature, but let me just again pause to see if there are any questions at this point. Otherwise, I'll tell you about this concretely. What is the behavioral model of expected utility maximization at accurate beliefs?
I think you can go ahead, Ashesh.
Awesome. So let me now start telling you concretely about this behavioral model of expected utility maximization at accurate beliefs. So first, what's the decision maker's information set? So for each decision, the decision maker will observe the characteristics X and then form initial subjective beliefs about the outcome Y star that I'll denote by the conditional distribution Q of Y star given X. So in that pretrial release application, recall that these characteristics include information about the defendant, such as their current charge and their prior arrest record. So this object summarizes the judge's initial beliefs about failure to appear risk as a function of these observable characteristics. Next, for each decision, the decision maker will observe a realization of their private information that I'll summarize by the random variable V. Now, because private information is an unobservable from our perspective, a key point of emphasis in my analysis is to place no distributional assumptions on this object and model it non-parametrically. So in the pretrial release example, private information is often thought of as extra information that the judge learns about the defendant over the course of the pretrial release hearing, but we don't get to see what happens behind those closed doors. Finally, the decision maker will then update their beliefs by applying Bayes' rule to their initial subjective beliefs and their private information, and then evaluates choices under their posterior. So the challenge here is going to be to somehow draw inferences about the decision maker's initial subjective beliefs using data on their choices, which reflect their posterior, leaving private information, its support, and its likelihood function unspecified. Next, what are the decision makers' payoffs? So now I'm going to assume that the researcher partitions the observed characteristics X into two subvectors, X0 and X1. And then the decision maker's payoffs are simply summarized by a utility function defined over choices, realized outcomes, and characteristics in X0. So in other words, it summarizes the payoff associated with each combination of choice C, latent outcome Y star, and characteristic X0. So now I'm assuming that the decision maker's utility function satisfies an exclusion restriction. That is, the characteristics in X0 directly affect choices through both the utility function and the information set, whereas the other characteristics X1 and private information V only affect choices through the information set. Now that's a substantive behavioral assumption because it implies that if we fix the characteristics entering into X0, any residual variation in the decision maker's choice probabilities across X1 only reflects variation in their posterior beliefs, not variation in their utility function. Now, let me also briefly argue that these sorts of exclusion restrictions are common in empirical researchers' intuitions about these sorts of applications. So for example, in the pretrial release example, it's common for researchers to at least start by assuming that a judge's utility function, the cost of releasing a defendant that would fail to appear in court or detaining a defendant that would not fail to appear in court, only directly depends on some limited set of characteristics, such as the defendant's race through a taste-based discrimination motive, defendant age, or defendant charge severity. And similarly, in analyzing medical decision makers, researchers are often willing to assume that a doctor's utility function does not directly vary based on observable patient characteristics, but these characteristics are nonetheless informative about underlying medical risk. So altogether, under the model, the decision maker is going to make choices to maximize expected utility given beliefs that depend on the characteristics X and their private information. So the question is going to be, how can we understand the empirical content of this assumption? So the way I'm going to address that is by noting that if we fix a utility function U, expected utility maximization behavior is actually an incomplete econometric model of choice behavior, meaning that it yields a set of feasible joint distributions over characteristics, private information, choices, and outcomes that must satisfy two conditions. The first is that choices must maximize expected utility given the decision maker's payoffs and their information set. And the second is that choices must be independent of the outcome Y star given the characteristics X and V or the decision maker's information set. In words, the second condition simply says that if the decision maker is indifferent across choices, she can randomize, but that randomization has to be independent of the outcome given their information. So in other words, X and V truly summarize everything the decision maker observes. So with this realization in mind, I'm then going to say that the decision maker's choices are consistent with expected utility maximization at accurate beliefs if there exists some combination of a utility function and an associated joint distribution Q under the model that could reproduce the joint distribution of the observable data. Now, that was a lot. So let me now sort of dwell on that definition a little bit more and talk to you about its interpretation. So the first thing to note is that if choices are consistent with expected utility maximization in that sense, it means we can find some combination of a utility function, accurate beliefs that lie in the identified set for the true conditional distribution of Y star given the characteristics X, a likelihood function and support for private information, and a tie-breaking rule that could reproduce the decision maker's choices. In other words, it implies that absent further assumptions, we could rationalize the decision maker's behavior as maximizing expected utility at some utility function, accurate beliefs, and some distribution of private information. For this reason, I'll say that the decision maker's choices reflect systematic prediction mistakes based on the characteristics X if their choices are inconsistent with expected utility maximization at accurate beliefs. In other words, in this case, there exists no combination of a utility function, accurate beliefs, private information, nor a tie-breaking rule that could have reproduced the decision maker's choices. So next, I'm going to briefly walk you through some of the core identification results in the paper. But again, let me just pause to see if there are any questions so far, because I went through sort of the setup of the model a little quickly there.
So maybe if so a more practical question. So for this tie-breaking rule, if you wanted to bring this to the data, I mean, maybe we'll see it later. So we'll need to have sufficient data for realizations in X and V, right? So in observables and private information. So I guess that's just typical, you know, when you go non-parametric, or is there?
Yeah. So what I'm going to show you next is basically the empirical content of this model is only going to depend on features of the joint distribution of the characteristics, choices, and selectively observed outcomes. So what we need to be modeling to sort of test whether those conditions are satisfied are going to be conditional choice probabilities and conditional expectations of the outcome given choices and the characteristics X, from which we can apply our, standard non-parametric regression techniques to estimate those. So in other words, we can, let me just jump ahead to that result, is we can profile out all unobservables from this model and only look at the testable implications over data we actually get to observe. But that's a result.
Okay.
Yeah.
Thanks.
So for the talk, what I'm going to do is I'm going to focus on an economically rich benchmark class of what I'm going to call linear utility functions, linear in the outcome Y star. So in the pre-trial release example, if we define this outcome to just be the binary outcome of whether a defendant would fail to appear in court, then this class of utility functions means that we are willing to assume that it is costly for a judge to release defendants that would fail to appear in court and detain defendants that would not fail to appear in court. But the way they trade off across those types of ex post errors may richly vary based on the observed characteristics X0. Now, if we instead define the outcome to be vector valued, which I do in some extensions in the empirical application, this also allows the decision maker to richly trade off across components of the outcome as well. So the question I'm going to narrowly focus on in the next slide is under what conditions are the decision maker's choices consistent with maximizing expected utility at accurate beliefs, any private information, and any linear utility function. So in particular, what I show in the paper is that the decision maker's choices are consistent with expected utility maximization at any accurate beliefs, linear utility function, private information, and a tie-breaking rule, if and only if, for all values of the characteristics X0 that directly affect the utility function, the following system of inequalities are satisfied. Now, before I walk you through the intuition of these inequalities, let me just point out one fact to you, which is that these inequalities only depend on the point identified conditional distribution of Y star given choices 1 and X, so in the application, the observed failure to appear rate among released defendants, and the unidentified conditional distribution of Y star given choice is 0 in the characteristics. So in that pretrial release example, the unidentified failure to appear rate among detained defendants. The implication is that the decision maker's choices are inconsistent with expected utility maximization at accurate beliefs, if and only if there exists no conditional distribution of Y star given choices 0 and X that satisfies the system of inequalities. So now what's the intuition of this result? The intuition is that over the class of linear utility functions, expected utility maximization requires the decision maker to make choices according to an incomplete threshold rule on their posterior beliefs or their posterior beliefs about the expectation of the outcome given the characteristics and their private information. So what this result is really showing is that expected utility maximization at any accurate beliefs in private information is in fact observationally equivalent to behavior generated by expected utility maximization under beliefs governed by these two inframarginal conditional expectations. So in other words, we only need to check whether we could have produced the decision maker's choices under a threshold rule on these inframarginal conditional expectations, one of which is identified from the data, the other which is not identified, but I'll argue that we can get informative bounds using quasi-experimental variation. And then let me just skip the sort of proof sketch for sake of time. But we can then use these inequalities to try to understand what exactly are the testable implications of accurate beliefs in this setting. And one immediate implication is actually a striking negative result, which is that at this point, under the assumptions that I've laid out for you so far, the decision maker's choices are always consistent with maximizing expected utility at some linear utility function, accurate beliefs, and private information. So in that pretrial release example, it means we can always find some configuration of costs of releasing a defendant that would fail to appear, detaining a defendant that would not fail to appear, accurate beliefs about failure to appear risk, and some distribution of private information that could reproduce a judge's observed choices. And the intuition is that over this class of linear utility functions, as I mentioned, choice behavior is equivalent to a threshold rule on these conditional expectations, as I mentioned, and we can always find such a threshold rule to rationalize behavior. Now, more concretely in the paper, I show that that negative result arises under two broad sets of conditions. The first is that if we make no assumptions about the missing data, this unobserved conditional expectation, or in the application, the unobserved failure to appear rate among released defendants, or we assume that there exists no characteristics X1 that only affect beliefs, but not affect utility, we make no assumptions about such an exclusion restriction, then we can always rationalize choices under this model at some linear utility function and accurate beliefs. So in other words, testing whether choices are consistent with expected utility maximization at accurate beliefs, identifying systematic prediction mistakes over the class of linear utility functions requires us to introduce two additional assumptions on the problem. The first are econometric assumptions to construct informative bounds on the missing data. And the second are behavioral assumptions that will exclude some observed characteristics X1 and private information V from directly affecting the utility function. In other words, at best, we can only test a joint null hypothesis about behavior that choices are consistent with expected utility maximization at accurate beliefs, and we have correctly specified the conjectured exclusion restriction about the decision maker's payoffs. Now, looking at the time briefly in the paper, I discussed how we could use quasi-experimental variation, such as an instrumental variable, to construct bounds on the missing data exactly as that form. But because that involves writing out a few sets of equations, I'm just going to skip those details, and I'll tell you that I apply these results in the empirical application coming in a few slides. So what exactly is the interpretation of those inequalities or violations of those inequalities that I wrote out on a few slides ago? So to walk you through the interpretation of what I'm going to be looking for in this pretrial release example, let me focus on a very toy setting where there are no characteristics X0 that directly affect a judge's utility function, and the remaining characteristics X1 only take 10 different values. So the first thing we can directly observe from the data is what is the conditional expectation of the outcome given choices 1 and the characteristics X1. So this curve in orange in the empirical application will map to the observed failure to appear rate among released defendants at each value of the characteristics X1. Next, let's imagine that we have done something, use some quasi-experimental variation to construct a bound on the missing data that I've plotted in blue, the unobserved conditional expectation of choices 0 and the characteristics X1, or in other words, a bound on the unobserved failure to appear rate among detained defendants in the empirical application. Next, the results I just showed you tells you that to identify systematic prediction mistakes, we have to compare various features of the bound in blue against the observed curve in orange. So to do that, let me just sort the x-axis in order of increasing risk. And now identifying systematic prediction mistakes is going to ask the following question. Does there exist some cell of defendants where the decision maker or of choices where the decision maker is selecting choice C equal 1 at a higher observed average outcome Y star, while at the same time selecting choice 0 at a lower worst case or upper bound on the average of the outcome given choices 0? So in other words, does there exist some cell of defendants that the judge is releasing at a higher observed failure to appear rate, while at the same time there is another cell of defendants that they are detaining that has a strictly smaller worst case failure to appear rate under our assumptions on the missing data? In this cooked up numeric example, clearly that's the case. And it means that the decision maker could exchange their choices across these cells and do strictly better, no matter their linear utility function and no matter their private information. In other words, they must be misranking decisions based on their own prior predictions about risk. But that intuition required us to assume that there were no characteristics x0 that directly affected the utility function. So now in this example, let's imagine that we had misspecified this, and there was in fact some characteristic x0 that took two values over which the decision maker's utility function varied. Now, the identification results tell us that we must only look for those same misrankings conditional on the characteristics x0. And if we did that in this cooked up numeric example, we would have actually found that there are no misrankings conditional on the characteristics that affect the decision maker's utility function. So in other words, the testable implications that we're focusing on here always arise from a joint null hypothesis about behavior, that choices are consistent with expected utility maximization at accurate beliefs, and we have correctly specified our conjectured exclusion restriction on the decision maker's utility function. So in order to have time to dive into how I actually use these results to analyze the pretrial release application, let me just very briefly say that these inequalities have very nice structure. They take the form of a system of many moment inequalities or intersection bounds, but a core econometric challenge is that the characteristics X take many different values. Their support is large. So in the paper, I discuss how we can use machine learning off the shelf to do dimension reduction on this testing problem and still have a nice interpretation as falsifying or testing for systematic prediction mistakes. But for sake of time, I'm not going to be able to talk to those results in details, but if people are interested in the Q&A session, very happy to talk about that more. So before I tell you about the empirical application, let me just pause again to just see if there are any questions that have come up in the chat. If not, I'll walk you through what I do in the pretrial release setting.
I think we all want to see the application.
Great, me too. So now let me tell you what I do in this application to pretrial release decisions in New York City. So first, let me just very briefly tell you about the pretrial release system in New York. So in New York City, judges have to decide whether to release defendants that are awaiting trial based on a prediction of whether they would fail to appear in court. So based on the jurisprudence in New York, that is the outcome that judges should be predicting. So to analyze judge behavior, I'm going to use a main estimation sample that consists of roughly 570,000 cases heard by 265 judges from 2008 to 2013. And I'm going to focus on analyzing the behavior of the top 25 judges that heard the most cases in the data. And these judges consist of roughly 50% of all cases heard in New York over this time period. So they represent the majority of the pretrial release system. So the question I'm going to ask is, are the pretrial release decisions of these judges consistent with maximizing expected utility at accurate beliefs about failure to appear risk given observed defendant characteristics? So I'm going to apply the identification results for this binary outcome of failure to appear risk or not. But in the paper, I discussed several other robustness checks where you could define the outcome in many other rich ways and apply the identification results for those alternative choices. So to walk you through the implementation, let me focus on a single judge in New York City whose pretrial release decisions that I analyze. So I'm going to plot various quantities over this judge's choices for different cells of defendant characteristics: younger Black defendants, older Black defendants, younger white defendants, older white defendants. So you should think of these four cells as a conjectured x0 across which the judge's utility function may vary. And then on the x-axis, I'm going to bin together all other defendant characteristics into a predicted risk decile, which is going to come from an estimated prediction function that is estimated on the decisions of all other judges not in the top 25. So I'm sweeping some details under the rug of where that comes from for now. So first, for this judge, we can observe their release rate at each defendant cell and at each predicted risk decile plotted in green. For this same judge, we can observe what is the failure to appear rate among defendants that they release, again, at each defendant cell and each predicted risk decile. So the concrete question I'm asking is, are these patterns of pretrial release decisions rationalizable as maximizing expected utility at accurate predictions about failure to appear risk, given some private information and a utility function that varies across these cells? To answer that question, the identification results tell us that I have to somehow construct a bound on the unobserved failure to appear rate among defendants that were detained by this particular judge in New York City. And to do that, I use the quasi-random assignment of judges to cases and apply those instrumental variable bounds that I didn't have the chance to talk through in more details to construct this curve in blue, which is an upper bound on the failure to appear rate among defendants detained by this particular judge at each defendant cell and each predicted risk decile. Now, the identification results simply ask us whether there are any misrankings in this judge's choices. And it turns out, based on the point estimate, the answer is yes. This judge is releasing defendants at the top of the predicted risk distribution at a higher observed failure to appear risk, while simultaneously detaining defendants at the bottom of the predicted risk distribution that have a strictly lower, worst case failure to appear risk. They could exchange their choices and do strictly better, no matter their utility function and private information. But now, of course, this plot is just based on point estimates. There's really standard errors around these quantities. So what I do more formally in the paper is I test whether there are violations in each judge in the top 25's choices under various exclusion restrictions on their utility function using off-the-shelf moment inequality procedures. So what I'm going to next show you is that for each judge in the top 25, I'm going to test whether their choices suggest they're making systematic prediction mistakes if we assume that no characteristics affect their utility function, only defendant race and age, or defendant race and charge severity affect their utility. And then really, because I'm going to be doing 25 different hypothesis tests in each of these cells, what I'm really going to report is the adjusted rejection rate after applying a really stupid multiple hypothesis test correction, the most conservative thing you could do, a Bonferroni correction. If you do that, what you find is that for at least 20% of the judges in the top 25, the implied revealed preference inequalities are violated. In other words, there exists no combination of a utility function that varies based on defendant race and age, arbitrarily, accurate beliefs in the identified set, any distribution of private information, nor a tie-breaking rule that could reproduce their observed pretrial release decisions. So given our stated assumptions, we could not rationalize their behavior as maximizing expected utility at accurate beliefs about failure to appear risk given defendant characteristics. Now I'm talking about this as a lower bound because you can implement the test in many different ways. We redefine the outcome to not just be failure to appear risk, but whether a defendant would fail to appear, be rearrested, or fail to appear, be rearrested for a violent crime or a non-violent crime. Redefine the choice to be not just release or detain, but release or set monetary bail, and use many other alternative strategies to construct a bound on the failure to appear rate among detained defendants. It turns out all of those other choices lead to larger rejection rates. So this is truly the most conservative estimate that I found in this application. Then in the last couple of minutes, let me just briefly tell you what I do in the rest of the paper. So I found that many judges make systematic prediction mistakes. I want to now understand where do these systematic prediction mistakes occur and why do they occur in this setting. So qualitatively, what I do next is I'll ask, where do the largest violations in these revealed preference inequalities occur? Do they occur over white defendants or Black defendants? And do they occur over defendants in the middle of the predicted risk distribution or the tails of the predicted risk distribution? It turns out that all of these violations, or the largest of them, occur over defendants in the tails of the predicted risk distribution and primarily over Black defendants. So in the next chunk of the paper, I extend the identification results to show that we can actually use that information to bound the fraction of decisions on which the judges make systematic prediction mistakes and how costly are the prediction mistakes to the judges in an expected utility sense. And finally, also make statements about the ways in which their beliefs are systematically biased. But in the last minute or so, let me just jump ahead to tell you what exactly are some of the policy implications that I find of this analysis of systematic prediction mistakes. So now, motivated by this behavioral results of that judges make systematic prediction mistakes, and they occur primarily on defendants at the tails of the predicted risk distribution, I'm going to now ask, what are the effects of replacing judges with an algorithmic release rule in New York City? So now let's imagine that we're a policymaker that wants to analyze outcomes in New York, and we specify our own social welfare function that summarizes the cost of detaining defendants that would not fail to appear and releasing defendants that would fail to appear. And we're going to compare outcomes under two alternative decision rules. The judges observe choices, and the second is an algorithmic decision rule that will threshold predictions of risk. So there's a bit of a detail here, which is that due to the missing data problem, expected social welfare is partially identified. So in the paper, I describe the identified sets and show how we can conduct inference on that object, and I'm going to apply that in the next few plots. So first, let's ask what would be the effects of fully replacing judges with an algorithmic release rule over all cases they observe in New York City. And so on the y-axis, I'm going to plot the comparison of outcomes in the status quo in a welfare sense against judges' choices versus the algorithm. So positive values means the algorithm dominates the status quo. Negative values will mean, in fact, that the status quo choices of judges actually dominates the algorithm. And on the y-axis, I'm going to be varying the social welfare function. So that's going to be summarizing how does this comparison of judge versus algorithm change as we change the social welfare function in this setting, the cost of releasing defendants that would have failed to appear in court. So if we do that,
Ashesh,
yeah.
Sorry, and here you measure welfare by the utility of each judge, right? That you've recovered. Yeah, okay.
Great question. So here I'm measuring welfare from the perspective of a policymaker. So the policymaker specifies their own costs of releasing defendants that fail to appear versus detaining defendants that would not fail to appear. And on the x-axis, I'm going to be varying the social planners or policymakers' welfare function.
Okay,
so this is going to be plotting how the comparison of algorithm versus status quo changes as we change the social planners' preferences. Yeah. So if you do that, what you find in New York is that the effects of full automation actually depend crucially on the social welfare function. So that is, for most values of the social welfare function, the algorithm dominates the status quo. But in fact, there exists a range of parameter values where the status quo decisions of these judges actually dominates the algorithm. So what's going on here? So as I discussed in the paper, judges in New York only appear to robustly make prediction mistakes over defendants in the tails of the predicted risk distribution. And you can actually rationalize their behavior over all of their defendants as maximizing expected utility at some preferences and some private information. So what this region suggests is that for these values of the social welfare function, judges' private information remains sufficiently useful that they make better decisions than the algorithm. But again, we can talk about that, talk about the interpretation of that in a little more detail. But the behavioral analysis actually makes a very crisp prediction about where automation would be most valuable. And that's over defendants in the tails of the predicted risk distribution, where there exists no utility function or private information that could rationalize the observed choices. So now what I'm going to do is I'm going to do that same comparison, but now compare the status quo against a counterfactual where we only replace judges with the algorithm over defendants in the tails where we uncovered systematic prediction mistakes to occur. And if we do that, we now actually find a striking strict dominance result, which is that for all values of the social welfare function, this partial automation counterfactual does at least as well or strictly better than the observed status quo choices of judges. So altogether, this is to say that understanding whether and where decision makers make systematic prediction mistakes, as I've defined in this paper, can help us understand where automation is most valuable in these sorts of settings. So now I'm, very much way over my 45 minutes, so I'll just put the conclusion slide up and see if there are any questions or comments so far. But to summarize, what I did in this paper is I tried to develop an econometric framework to analyze systematic prediction mistakes and then applied it to analyze the choices of judges in New York City, although the results in this paper I think are more broadly useful in an array of microeconomic applications of interest. So let me stop there and see if there are any questions, comments, or reactions. Thanks.
Thanks a lot, Ashesh. This is a fascinating talk. So we do have a couple of minutes for quick questions. So we don't have any in the chat. So if anybody wants to ask a question, feel free to raise your hand or unmute. I have another question, but I'm very happy to leave the floor to the audience. Elliot, go ahead.
Maybe this is like part of this last bullet you have there. Have you started working out or thinking about if the prediction was given to the decision maker, what that would tell you. Because I mean, I guess like they have these papers showing that even when you give the risk scores to judges, they don't use it.
Yeah.
And so what do you make of that?
Yeah, so as the last bullet point alludes to, sort of the way these tools, just to zoom out a little bit, the way these tools get implemented is they get implemented sort of first sometimes as a triage step. So we make our own predictions. If a defendant in this criminal justice application is sufficiently low risk, we'll automatically release them, or sufficiently high risk, they won't go in front of the judge. So the results I was showing you on the previous 2 slides are about that initial triage step. But then oftentimes they'll still leave judges in the loop for the remaining defendants, but offer them a recommendation or a risk score. So I think to think about that and to really think about that formally, you now have to sort of model how does the decision maker react to the introduction of that information. So in other words, do they treat that just as information itself that they condition on in their beliefs? If they do, and they have accurate beliefs, risk scores are just a function of observable characteristics that they get to observe. So if a decision maker has accurate beliefs, the risk score should not affect their choices. Empirically, we don't see that, which is suggestive that there is some bias there. But there's also stories you could tell where basically the introduction of a risk score affects decision makers' utility function or preferences of themselves. They're sort of being told that the policymaker would like to make a particular decision that may affect the way they assess the relative costs of release or detention in this example as well. So it's a long way of saying, I think it's not really clear to me how, if you take this sort of perspective motivated out of decision theory, how you would even model that. I have some loose thoughts about how to do it, but I think that is kind of the next frontier, because what we've seen over the last 3 years is, again, as Elliot was alluding to, there are many really wonderful empirical papers that show the introduction of these tools affect choices in entirely unexpected ways. They are designed to reduce disparities, but they actually magnify disparities. When decision makers override them, they override in ways that actually make decisions worse effectively. I think writing down formal frameworks to talk about the optimal design of decision support is really what this literature needs to do next.
I think the explainability issue is super interesting, just to think, which if you give them a summary of the prediction and like which factors are driving it, like is that going to help? I think that's an interesting open question.
Yeah, the way I think about it is, I didn't get a chance to talk about the results here, but one sort of concrete question we can ask is, given the data we get to observe, can we say something about the mechanism for their prediction mistakes? So one story is that judges, for example, are inattentive. They pay attention to some limited set of information because they have to make a lot of these decisions quickly. And if that is sort of the correct explanation of bias in this setting, it may suggest how we want to design explainability or think about explainability in a more sort of grounded sense. If the problem is decision makers are inattentive, explainability may mean we want to draw their attention to stuff that they do not actually pay attention to. So that's another tie-in where sort of thinking about the mechanisms may help us sort of do better in thinking about these problems. Yeah.
So that's a super interesting discussion, and I'd also have a comment on that. But actually, Aileen and Nielsen, I'd like to relay a question at first. She doesn't have a mic. So could you comment at all on learning or shifts in preferences? Yeah, have you read that? And over time?
Yeah, I just saw. It's a fantastic question. So it's not something. So let me answer this in 2 ways. So one is I'm sort of treating this as a static problem. One way you could think about learning using my results is to now define the decision maker in the application as a judge by year. So it would be Judge 302 in 2008 versus Judge 302 in 2009, 2010, et cetera. And then ask, how do your conclusions about prediction mistakes vary over time? Does it look like they're making mistakes in the beginning of the sample, but those mistakes appear to go away which would be suggestive that they are in fact learning something about the relationship between risk and outcomes. It's a great suggestion. It's something I haven't actually done in the data, but is the next thing for me to do on the to-do list. I think more foundationally, it's a very interesting question of how you would sort of model dynamics and learning in these settings. This is now me putting on my econometrician hat. In other words, what are if you sort of thought that decision makers face this sort of dynamic explore exploit trade-off, does there exist conditions under which you could rationalize their behavior as learning or not learning, or in a sort of optimal sense? To my understanding, that is an entirely open question in these sorts of environments. And it's, again, coming back to this last bullet point, I think these sorts of applications where computer scientists and data scientists are now, there are papers where they ask, what if you replaced a doctor or a hiring manager with a bandit algorithm? How would you do? These papers are kicking off, like, to me, fascinating questions about the identification of sort of decision-making behavior that just have not been studied. And to me, it's pure white space. So it's a fantastic question. I'm sorry, I don't have a better answer for you.
Thanks a lot. All right. So now we're